Before I start this video, let me take 30 seconds to tell you something about Exergic. Exergic is India's most trusted and most experienced institute for online GATE preparation. I am Chandresh Mahajan, founder and chief educator at Exergic. I am an All India rank 37 in GATE Mechanical Engineering, an ex-Indian Oil officer having 7+ years of teaching experience as of now. These are the GATE 2021 Mechanical Engineering toppers from Exergic. You can find their preparation strategy on Exergic's website. To know more about our GATE courses, you can visit our website or contact us on these details. Also, you can download Exergic GATE preparation app from Google Play Store. The link is available in the description of video. Now let us understand this problem, which looks very easy when you look at the image, the diagram given to you, which looks very simple when you read the given data. But once you start solving it, you will realize it is not that usual question that you are having the habit of solving, right? I know this type of question. When you will read the question, you will realize that similar language, similar diagram, you might have solved many times, very simple question. But please understand that this is not that question. This question looks very simple and easy, and it is, but with a very good twist, which makes this problem very interesting and very important. Let us have a look at the question. A tensile force P is applied on a bar which is 60 mm wide and 10 mm thick as shown. So as we can see here, there is a bar which is having a width of B, right, and a thickness of T. Width is 60 mm, thickness is 10 mm. Basically, if this is the top view of the bar, then this is the width 60 mm, and if you look at it from the side, this is the thickness, this one, which is 10 mm. A force P is being applied on that bar, right? Ideally, when you apply a force only from one side, it will displace, right? But since from the other side, you can have some support to give it a reaction. That's what is happening here. As you can see that there is a hinge present. From the top view, you can get an idea. From the side view, definitely you can get the idea. And we are trying to apply the force P, but there is a pin which is passing through it, which will give it a reaction. We already know how a hinge gives a reaction, right? This is something which is the basics of strength of material, which we have already covered, right? It does not resist the rotational motion, but obviously if you try to displace it, it will give opposite reaction to that, right? So stress is going to be there. As it says, the bar is hinge supported by a pin of diameter D, which is visible to us, D diameter, and this is also D, right? From the top view also, you will be able to see cross section, and from the side, you will be able to see the length. So this is the pin, this is the hinge, using which we have supported it. It is having a diameter of D. The pin passes through the same size hole in the bar. Okay, so there is no gap in the size between the pin and between the bar. The allowable tensile stress on the net cross section of the bar is 140 megapascal. So this bar is made up of obviously some material which is having allowable tensile stress or strength on the net cross section of the bar as 140 megapascal. Okay, because any material can have different types of stresses, allowable stresses. In tension, it will allow some stress, some magnitude. In compression, some magnitude. In shear, some magnitude, right? So for the tension, this material will allow this much of stress, 140 megapascal. Material of bar. The allowable shear stress in the pin is 80 megapascal. So this, obviously due to this force P, this will try to shear away. This will also try to shear away this, right, cross section of the pin. So shear strength of the pin obviously is going to be important. So shear stress, allowable shear stress is 80 megapascal for the pin, right? And the allowable bearing stress between the pin and the bar is 200 megapascal. As we know, as we have covered, bearing stress is same as compressive stress for this discussion. So allowable compressive stress between the pin and the bar is 200 megapascal. The bar is trying to move in one direction, but since pin is in contact with the bar, right? So both of their surfaces are trying to press against each other, right or not? This bar is trying to move in that direction. But from here up to here, right? That surface which is trying to push the pin is not moving anywhere. Pin is at its own place. So they are going to press against each other, right? Compress against each other. Again, this is not something that we are knowing for the first time. Whole concept behind this we already know. Other than 2-3 types of stresses, more number of stresses are possible, right? Even the shear stress in the bar is also going to act. We know that for such case, shear stress in the bar also going to act, right? But in this case, has the question given you shear stress in the bar, the allowable shear stress? No. It has only given you its allowable tensile stress. So you only have to take those cases as I have told you where the data is known to you. If question has not given you the shear stress of the bar, then the shear of the bar from here and here, that you don't have to consider, right? So I am not repeating those concepts here. In case of bearing between the pin and the bar, what areas are going to come? Projected area is going to come. So all those concepts will be used here. But again, these are the concepts that are basic that we have already covered. Now the question says that find the pin diameter for which the load P will be maximum and also find the corresponding value of the maximum load or maximum load. So far the questions that we were solving, what we were doing in them? Generally, that diameter was given to us and we were asked what is the maximum allowable value of force that we can apply. But here things are slightly opposite. It has not given you the diameter of the pin. Rather, it is asking you, find out the diameter, and it has not given you the P also. It has not given you, means it has neither given you diameter nor given you force, and it is asking you that you tell what should be the value of diameter, pin diameter, for which load P will be maximum. Also find out the value of P. So although up to here, up to this point, question was looking very direct, but now you would have started to feel ki something is different in this one, right? So let's start. This is just an enlarged view of the given diagram so that you can see it better. B is 60 mm, and right now I am expecting that you have started trying to solve the question. I am expecting that you are not just sitting and watching this question like a movie, right? I am expecting that you have started to try this question. I have also written the 3 allowable stresses that has been given to us. The first case we are going to pick, we will find out the equation for that, then the second, then the third, right? That's how we do such question as we have done earlier. So for the first case, we have to consider the allowable tensile stress on the net cross section of the bar, which is 140 megapascal. Now in the bar, we have 2 different extremes of cross sectional area of the bar. One is without the hole, means this one, a complete cross section, and other one is with the maximum hole diameter, right or not? Because there will be different section. There will be this section also, which is having not the complete diameter but only some part of the pin, right or not? So that circular hole has different sections, right? As I told you, we are going to consider extreme section here to compare. So which is the extreme section? This is the extreme section, this one, right? Which is passing through the center of this hole, right? That section has minimum cross section area. This has full cross section area, but the section passing through the center will be having minimum cross section area, as I have again already explained you, already showed you, because it has the maximum size of the hole. So the area, cross sectional area, which can actively resist in tension, that is how much? Effective width multiplied by thickness. Effective width is B minus D multiplied by T. That is the effective cross sectional area resisting in tension, multiplied by allowable stress in tension. That will give you the value of P in tension, right? So as we have done here, the tension in the bar The expression of that you can find out by sigma t multiplied by area. Area is b minus d multiplied by t. Now, PT we have written. As we know, this PT is not some other value of P. It's the same value of P. But this same P we will find for different cases. For tension, compression, shear, or if other values are also given, accordingly 4 or 5 different values we will find. So this PT is some value of P only, right? When we are only analyzing the tension in the bar. So sigma T multiplied by B minus D, sigma T is in megapascal. So if we are keeping the stress as we know in megapascal, keeping the dimensions in mm, then the value of force that we calculate is going to come to Newton, right? A very simple but very useful funda used everywhere in strength of material, in theory of machine, in fluid mechanics, machine design. So here this is in megapascal directly. D value is 60, D value is not known to us, rather we have to find out the value of D, multiplied by T is 10, okay. So this will become 1400 multiplied by 60 minus D Newton. Got it? This is the value of PT. Similarly, we are going to find out the value of shear in the pin. Since this force P being applied on the bar, this bar is trying to chop, cut, shear the pin, right or not? From where? From here and from here, right? If this pin was made up of butter, and if you move the bar, it will simply cut it from here and here, right? But it is not made up of butter, it is made up of the metallic material, some metallic material. So it is going to offer some good value of shear stress that we can find out by these two areas, right? So the allowable value or the value of PS here, as we have written, is tau s multiplied by area. Tau s is known to us, it's 80 megapascal, 80 megapascal. Area is 2 times of cross-sectional area of pin, not to be missed. Some of you will forget this. I know it's a very less common silly mistake, but trust me, it can happen. So very careful, whenever shear stress comes, very careful, check which areas, different areas are resisting, right? So here it's 2 multiplied by pi d square by 4. Again, if you put 80 here, it will become 160 by 4 means 40 pi d square. Put the value of pi and multiply. If you don't want to multiply, you can just leave it there also, but I have done it. So 40 pi is equal to 125.664 multiplied by d square Newton. This is the value of PS. I am sure up to this point, nothing is new, nothing is difficult. Consider discussion up to this point, just like a revision, right? But real thing is yet to begin. The real thing is yet to begin after this slide. Now, considering the third case of compressive or bearing between pin and the bar. So this pin and the bar, they are going to, as we know, have bearing interaction, compressive interaction with each other, which is calculated by projected area, right? Not the actual curved area, but the projected area of that. The reason behind that and all we have already discussed, so I am not repeating it here. So that one is equal to this D multiplied by T. If you look at the area, curved area, which both of them are interacting with, is this like this part, right? Half of this part. So it's like a curved area like this. So the projected area of that is going to be, this one, which is equal to this diameter, this one, multiplied by the thickness T, right? So D multiplied by T, as again I am telling, which we have already covered, is the area here. T is known to us. How much is T? T is 10 mm. So just put 10 here, you will get 2000 D. Sigma C is 200. Allowable bearing stress was 200 megapascal. So 2000 D Newton is your PC. So you have got the three values. You have got the PT, you have got the PC, you have got the PS. Now what we used to do earlier, we were knowing the D values earlier, right? So we'll just put the D values in all the expression and we will see which one of them is smallest one, right? That is the safest one for us. And generally that would be our answer. But here it's not the case, D is not known. Now what do you think? What can we do here? What can we do here? How can we find out the diameter for maximum P? How do we decide which P is maximum, right? So up to this point, all we have is these three expressions, and we need to find out, as we know, the value of D for which P will be maximum. Let us try to plot these three expressions on this graph. In this graph, we have diameter D here on the x-axis. On this axis, we have P. Why are we plotting it? That we are not going to understand right now, but in next few minutes, you will automatically realize, and I will also explain that why we did that and why this step is extremely important. The first expression, it looks like an expression of a straight line, right? Y is equal to mx plus c. You rearrange, you will get some values here. When the value of D is 0, P will be maximum, maybe somewhere here, right? D is 0, then 1400 multiplied by 60 Newton is P. And when you will keep on increasing the value of D, it will reach 60, then this term will become 0, P will become 0, PT will become 0, right? Maybe let's say here at D is equal to 60, P value will become 0. This is a straight line, as we can see from here. So let's say this is how the line of tension is going to be made. Coming to the line of compression first, 2000 D, very simple, Y is equal to mx plus c. Here C is 0, M is 2000. So when D is equal to 0, PC is 0, and as you will keep on increasing the value of D, this value will keep on increasing further and further, right? So let's say this is the equation of compression. Coming to this second one, which is somewhat like Y is equal to mx square, right? Or rather Y is equal to ax square. So there, if you look at it, it's going to be an equation like this, equation of Y is equal to ax square, something like this. Let's say this is the line of shear. When D is 0, P is 0, and obviously you will keep on increasing the value of D, and using this expression, the value of shear, the value of P is going to increase. So these are the three curves that we have plotted. Now what we used to do so far in other questions, we were given a value of D, diameter. That if this is the pin diameter, like width and thickness, diameter was also known to us. Then how much will be the maximum value of P that you can apply? How much will be the maximum value of P that you can apply, right? What we were essentially doing, that on this such a curve, we were given a specific vertical line or a specific value of D, having a fixed value of D. And for that line, if I draw just a straight line here, for that value of diameter, for a given value of diameter, this line is representing a given value of diameter. We were finding out whether PS is more, whether PC is more, or whether PT is more, right or not? This curve is for PS, for PC and PT, right? So for a given value of diameter, we were comparing all three of them. And when question was asking what is the maximum allowable value of P, then you were picking the minimum of them, not the maximum. Maximum one, we know that in technical discussion, in the discussion of strength of material design and other such subject, when we discuss about maximum allowable value, it means it should satisfy other values as well, right? So if the tension failure is going to occur at 10 Newton and compression failure at 20 and shear failure suppose at 30, question asks you what is the maximum allowable value of force. 30 is not going to be the answer, 10 is going to be the answer, right? Minimum value, because after 10, tensile failure will occur. So you can't say no, shear will stay at 30. Anything failed means it has failed now, right? Again, not something that we are discussing for the first time. This is a concept that throughout strength of material, machine design, fluid mechanics, we have covered. So the point here is that whenever we were solving such questions, we were not drawing any graph because there was no requirement as such. But essentially what we were doing, we were selecting any one of these points, this one or this one, for a given value of diameter, right? We were not drawing the graph, we were using concepts to get to the answer. But essentially this is the thing that we were doing, that ultimately we were deciding one coordinate, one point on this graph, which we were calling as the safe point and proceeding with that. The issue here is, in this case, what is the issue? Issue is that for this value of diameter, shear 1 is least, PS is least, and PT is maximum. But if you keep on changing the value, if you keep on increasing the value of diameter, things will change. A point will come when PS and PC, let me rather clear this first. A point will come when the value of PC and PS, shear and compression, will become same. But this will be again at the highest value. Again, if you keep on increasing the value of diameter, a point may come where shear will be the highest and tension and compression will become the same. So which value is maximum? You cannot decide if D is not known to us directly, right? But this graph we can use now to understand which one of them, which point in this whole graph we have to pick to find out the maximum allowable shear stress. That is my point here is, you need to understand that. Expand the horizon of your understanding, and please understand that in such questions, essentially what we are doing is selecting a point on this graph. Although we don't actually select a point in the graph, because not all questions require you to draw this graph and solve it. But essentially this is the graph that we solve in such questions. Although we apply the concept, as I told you, for a given diameter, we just draw a line and we pick which one of them is minimum as the safest one, right? We don't see the graph, we don't require the graph, but essentially we are picking a fixed point in this graph. Question is, which point would you pick in this graph when D is not known to you? And for that, you need to again understand one thing, basics of strength of materials, of machine design, that whatever expression we have applied here, all these expressions, what is PT? What is PT representing? Is the PT value fixed? A fixed value always equal to sigma T multiplied by area, because sigma T is a fixed value and area is also definite here, right? For a given diameter, area is also definite. So does this mean PT is a fixed value? No. What is PT? PT is telling you how much force you can apply so that you stay within the safe region. PT value in reality, this one, exactly this one is PT max. The maximum allowable force, considering the tensile failure of this plate, is this one. Not any value of P. If I want to write a generic expression, a general expression, then that expression would be PT should be less than equal to sigma T multiplied by area. Sigma T multiplied by area is telling you the maximum value of PT that this can sustain, this bar can sustain as a tensile load. But obviously the value of P can vary. Why are we talking about variation right now? Because we are in the graph where every variation is possible. So in the graph, we know, or by the concept also, we know that the value of PT can be less than sigma T multiplied by area also. This is just telling you the maximum allowable force that it can bear, right? It does not mean that PT has to be equal to always PT max. You can apply a smaller force. Perfectly okay. It will remain safe, right or not? So the point that you must understand, not only in this question, general concept that you know, that we have discussed, but you must realize is that this expression is specifically for maximum allowable force. Generic expression is not an equation, it is an inequality. Means the value of P, if you want to keep it safe, it should be less than sigma T multiplied by area. Maximum value at the boundary is sigma T multiplied by area. So same is true here also. This is also an inequality. Same is true here also. This is also an inequality. So basically here also these three are inequalities and not complete equations. if we want to consider all the cases of P, right? Here we are open to P, least value, maximum value, whatever we want to consider, we can consider here. I know we have to find out maximum P. We will come to that. I am not saying that we will not find maximum value. I am just making you realize that these are not equations, these are inequalities. Unless and until you write PT max, this is an inequality. And this concept is extremely useful in many numericals like this one, and other than this one also. Many such numericals are there. So here now, I don't have three equations, I have three inequalities that I need to plot here. And this is the interesting concept here, which you realize is a very essential concept of industrial engineering, linear programming problem, graphical method, right? Almost all the problem in that unit, the first unit of industrial engineering, linear programming, one of the very important units. Every year, almost every year, question comes from that. So in all those questions, we apply this concept, the same concept of LPP. This is a linear programming problem that has been given to us. You have three constraints. The PT value should be less than this, PS value should be less than this, PC value should be less than this. To maximize the value of P, right? P can be any of these, highest value, any of these. If you have not covered industrial engineering so far, you may not be able to take the full feel of what I am telling you. That's why I will highly recommend you write it down in some of your notes or reminder. And once you have covered the first unit of industrial engineering, do watch this example once again. It will open up your mind to the application of linear programming problem of industrial engineering, that how even a core concept of strength of material is so much related to the concept of industrial engineering, right? So this is the LPP that we have right now that we need to solve. Now before we start solving these three inequalities, obviously we need to plot them correctly. Now plotting PT or T, tension line or compression line, is basically very simple, straight lines crossing each other. At what point they are crossing, that also we can find out, right? By equating the two values. Equating the two values, we can find out the intersection point, right? The thing that you need to realize here is that we are not sure whether PS is going to pass from here like this, or maybe it is going to pass from the same point, or maybe it will pass from a point ahead of that, right? So where exactly is it going to cut the compression line? Whether it's going to be here or at this point or ahead of that point, that we don't know. And we must know that, only then we can actually solve the LPP. So in this case, let us first try to find out whether this line of shear is going to be before this point, at this point, or above this point, right? This value of diameter. So for that we need to find out this value of diameter, right? How can we find that out? Equate the two, only the equations, this part, this is equal to this. Basics of mathematics, school level mathematics. So if we equate both of them, I am not getting into the small calculations, that's why I have done that here. You can do that on your own. So here if you just solve them, you will get the value of ds 24.706 mm, right? I have just equated them. So this point I have got, how much? 24.706. And now to check whether the shear line is passing before or after that, what can we do? We have equated that, the shear line, with the compression line. So when we equate that, we got a quadratic equation. So if we solve that quadratic equation, 2 points we will get, because the shear stress line is crossing the compression line at 2 points, here and here. That's what we have got. If you solve this quadratic equation, d is equal to 0 is also possible, and d is 15.915 is also possible. Obviously this is not of our concern, we know they are intersecting there. This value is interesting to us because it confirms that yes, this point, the other point where shear and compression lines are intersecting, is equal to 15.915 mm, right? Which is before this. So we can say that the graph that we have made is correct. Otherwise we would have drawn it like this. If it was coming out same, then we would have drawn it like this. It matters. It matters in the question. You will see how. Coming back to the question, that these are actually inequalities. These are actually inequalities, as we know from here, right? So we want to plot those inequalities, and inequalities are areas, right? So for this line, tension line, this line is dividing the entire area into two parts, one on its left, other on its right. If we pick any value of d, there are many ways to plot this inequality on the area. I'll just talk about one. So if we pick any point d here, and for that d line, just analyze this tension line. This point is having equation of 1400 multiplied by 60 minus d, right? But inequality means values not only equal to that but also less than that. So this entire area is representing this inequality, right? Similarly, I am just going to show it by a single line like this. This concept you will find extremely useful in industrial engineering and operational research. Similarly, PS value you can find out in the similar way. This is the shear line. This is the point which is representing exactly this value. You have to select the values lesser than that also. So this area on this side, that area is going to denote this inequality, right? So again I am going to just use a single arrow for that. Similarly, this one is also going to behave in the same way. For any value of d, this is the point that represents 2000 d. We have to select the values less than that also. Means this area below this line, this entire area also you have to see, right? So basically these three areas are represented by these inequalities. One is this one, other is this one on that side of line, and third is on the below of this line. Again I am coming to the basics. Basics says that to solve this equation means what? How do we solve two lines? We find out the point which is common to them, right? That's what we did. That's what we did here. How did we solve two equations? We found out the point common to them. We equated them and we found out the common point, right? These are lines and common thing is a point. But these are not lines. Inequalities are areas. So you have three areas and common thing between them would be area. One area, two area, three areas. What area do all of them have in common? That area you need to check. That area you need to check here. Which is going to be equal to this area, right? Because we selected this line, this area on the bottom side of tension line. Similarly, area on the bottom side of compression line. Similarly, area on the bottom side of the shear line. This shaded area is going to represent the common area out of them. Obviously, it's going to extend. This line is going to extend further and meet at x-axis. Now again I am repeating, if you have not covered industrial engineering, you might be thinking that it's very difficult. But it is not. It is not difficult. Doing this manipulation is going to be very easy for you. Once you cover industrial engineering, that's what we are going to do in the first unit. And that's why you need to again realize the connection between that concept and this concept. Essentially what you have in such cases are inequalities. When question has given you diameter, it has made inequality an equation because it has specified the points, right? But it does not mean that always it's going to be specified, right or not. So please realize that you should be open, you should be ready to consider inequalities and use them in questions. Theoretical questions also are asked, numerical questions are also asked, and this is one example how numericals can be asked. You might be thinking that it's so detailed. It is not. You might have not covered industrial. That's why you might be thinking it is detailed. But what have we done so far? We have just put the values and got these equations. How much time it takes? Maybe 45 seconds max, 30 seconds, right? And then we have solved the 1 and 2 equations, quadratic equation, again 30 seconds each. So if you just start solving, sit and start solving, it's a matter of 2 minutes, right? So far 1.5 minutes, 2 minutes, but you must know what you need to do, right? That's the point here. Anyway, coming back to the point that we have found out that in this case, this area is going to be the common area. This area is going to be the common area below all of them, right? below the tension line, below the compression line, below the shear line. So this area is common, which is going to be present in all the areas. Common areas means solution of inequalities, right? So now what we have to do here, we have to come back to what the question was. Question was, what is the maximum value? What is the value of D for maximum value of P satisfying these conditions, right? Means satisfying these conditions means in this area, because this is the area which is satisfying these conditions. Again, I am repeating, these are inequalities, right? So how do you do that? In this case, again by the concept of industrial engineering, we are going to pick the corner points. This one, this one, this one, and the further one. These are the 4 corner points of the common area. Again, a concept from industrial engineering. If you see there, this point is having coordinate of 0, 0. The point on that side is also going to have some diameter and comma 0. Basically, the value of P is 0 for them. We have to find out maximum P. So these 2 points are not going to qualify, are not going to be considered. This point and this point, these 2 points are going to come now. Obviously, which of them is belonging to higher value of P or highest value of P? This one. This one, this one. This one is representing the highest value of P. So you need to find out this value of diameter, which is going to give you the maximum value of P, satisfying all these 3 inequalities, right? That's what we have done. We have found out the value of diameter for maximum value of P in the common area. Means satisfying the 3 equation. Common area means satisfying the 3 equation. So in the common area, which is the maximum value of P? And what is the value of diameter for that? That only we need to find out. And what? Guess what? We have already calculated this point. This point we have already calculated here. The intersection point of tension and compression, which is 24.706. That's our answer. That is our answer. The value of diameter for maximum value of P is 24.706 mm. And to find out the P max, put the value of D in any equation. Any? No, not any. Either of tension or of compression, not in shear. If you put in shear, you will get this value maybe, which is not satisfying other conditions, right? So you have to put the value for this point, which is either on the line of compression or on the line of tension. So any one of them you can pick, put the value, and you will get the maximum value of P max, which you can have satisfying all the 3 conditions. This question, again I am repeating, don't think that what we understood or what we learned from this question is only for this question. The concept that the expression that you have of P is equal to sigma multiplied by A, such a basic expression, have we used some very complicated expression here? No, the most basic expression that you cover maybe in the first unit of strength of material, that we have used. But we have extended that use in practical application, right? That actual value is less than equal to sigma I. So it is essentially an inequality, although we consider the maximum values only for our discussion in many cases. Or even if we don't want to consider the maximum value, question is asked in such a way that we don't even require other values. We don't require to solve the graph. We can just solve them, the 3 of them, and pick the highest or minimum of them. But when you don't know the value of D, when you don't know the value of maybe P, in such cases, you need to come back to the realization that these are in fact inequalities. And now, if you have not covered industrial engineering, you may feel that this is something which you don't know about. But again, this is not something which you are not knowing from the basics of mathematics. So if you knew from basics, well and good. If you didn't know from basics, this is something that we cover in industrial engineering. So even if you have understood this, but I will again recommend you to cover industrial engineering's LPP, write it in your notes or reminder and come back to this problem. You will realize that essentially such problems, the problems of strength of materials in practical applications, are LPP only, subjected to different constraints, where we may require to maximize or minimize some parameter.